In this project, we propose a novel system to continuously capture high-resolution shape of a moving human face and show how this data can be used to model new expressions and create new animations. Our system consists of a set of video cameras and data projectors. 2 DLP projectors are used to shine stripe patterns onto a subject. 4 black and white cameras are used to reconstruct 3D shape from 2 sides of the face. 2 color cameras are used to capture surface texture. The cameras are synchronized with the projectors at 60 frames per second and recorded at a resolution of 640 by 480. During face capture, we project a series of random black and white stripe patterns onto the subject. In addition, we shine ambient light using both direct and indirect illumination. Here we see the videos recorded by the cameras. The projection sequence consists of 2 frames of stripe patterns alternating with 1 frame of solid black. During the projected black frame, the subject is illuminated by the ambient light. We seek to reconstruct shape of these ambient frames where the color texture is best. Given the black and white stereo pairs, we can reconstruct the shape of the face over time. Here we compare 4 stereo reconstruction methods. On the upper left, we apply traditional stereo to each ambient frame independently. The lack of detailed texture results in a very noisy reconstruction. On the upper right, we apply traditional stereo to each pattern frame independently. The projected texture significantly improves the reconstruction, but it is temporarily noisy and no longer aligned with the color frames. On the lower left, we apply space-time stereo at each ambient frame. Space-time stereo integrates stripe information from neighboring frames, yielding high-resolution shape with greater temporal coherence. However, some striping artifacts arise from overfitting. Finally, on the lower right, we show our new space-time stereo reconstruction, again at the ambient frames. By enforcing global consistency constraints, the new method avoids overfitting and substantially reduces the striping artifacts. After reconstructing shape from the 2 stereo pairs, we have 2 sequences of depth maps aligned with the 2 color video streams. We now seek to compute a time-varying mesh whose shape matches the depth maps and whose vertex motion matches the optical flow between successive frames of the video streams. We start from a generic face template and first manually identify corresponding features. We then compute a global warp of the template to match the feature correspondence. This warp template is used to initialize the fitting process. After the warp, we no longer rely on the manually identified correspondences. Next, we compute a displacement for each vertex of the template mesh using a regularized objective function that optimally fits the template to the depth maps. Here we see the fitted result. The fitting is inaccurate over large regions of missing or unreliable data. We crop out these portions of the template mesh. Given the fitted template at the first frame, we computed displacement for each vertex of the template mesh to fit the depth maps at the second frame, while optimizing the displacement to be consistent with optical flow. We repeat this process for each frame of the sequence, using the computed displacements from the previous frame to initialize fitting for the next frame. After fitting is complete, we have a sequence of meshes with vertex-to-vertex correspondence. On the left, the sequence is shown as a gray shaded rendering to convey the captured geometric detail. On the right, the meshes are rendered with the acquired color. Here, we see the results of capturing and reconstructing a fitted mesh sequence for a female subject. This sequence consists of 330 meshes, each with about 15,000 vertices. We have created a tool that allows the user to edit a face in real time with intuitive controls derived automatically from the input face sequence. When the user places a control point, the locations of that point in the input sequence appear as blue circles. By moving the point around to these circles, the user can explore the expressions in the input sequence. Exaggerated expressions can be created by moving a control point beyond the scope of the blue circles. The user can create new expressions by placing multiple control points. The face is automatically segmented into regions that can be posed separately and blended into a single expression. One way to animate the captured face is to use video texture techniques to automatically generate new face sequences from the input. By changing the frequency of transitions between expressions, we can make the face more dynamic. We can also use control points to segment the face into regions that can be animated separately, then blended into a single animation. We have also created a keyframe animation tool. First, the user creates keyframes with our editor. Our tool then fills in the intermediate frames using data from the input sequence. Compared to linear interpolation, our data-driven technique can produce motion that looks more natural. Alright, time to check the old email. Whoa, a message from SIGGRAPH. Let's see. Congratulations, your paper has been accepted to SIGGRAPH. Subject to the following conditions. Your face capture results are nice. However, your algorithm is obsolete. Please re-implement using spherical harmonics. The paper is technically sound, but face modeling is a well-studied area. Please focus on toes instead. You have 2 weeks to revise. We also feel that your title doesn't accurately reflect your work. We suggest that you change it to From Head to Toes, a globally consistent, structured, photon-based approach for modeling, animating, and tanning using spherical harmonics.